Perfect. So thank you again for organizing this workshop. Haptics is definitely hot in today's XR spectrum, and I enjoyed hearing the future of haptic research from my colleagues. Uh, in this talk, I will give my perspective as being part of the industry and the challenges I had experienced while working as a haptic researcher, or Oliver Schneider said, haptician, in the last 10 years or so in this XR landscape. To introduce myself, I am Ali Israr from Facebook Reality Labs Research, and I will talk about challenges in haptic technologies to enable XR interactions. Mhm. Wait, I need to do something. Okay, I have to get rid of this guy. Okay, now it seems to be working. Sorry about that, guys. So before we start, maybe some of you also wonder what is XR. And first time I heard this term was back probably in 2013 or 2014. At that time, I was working on haptic technologies for AR and VR, and was trying to wrap my head around mixed reality spectrum. Since then, I went through several interpretation of XR, and recently, Mann and colleagues explain XR in the context of a in the context of a mixer metaphor of mixed reality, where one extreme is the real world and the other extreme is the complete virtual environment, and X defines the point in a continuum between the real and virtual realities. So Wikipedia also defines XR as a form of a mixed reality environment that comes from the fusion of ubiquitous sensor actuated networks and share online and and shared online virtual world. It further suggested that XR is a far-reaching, inclusive, and flexible term. The X represents the variable that defines the continuum that can also be expanded and extended in a multivariate sense. So, as the definition of XR is refined and evolved with time, my interpretation of XR interaction is that it optimizes the flow of information inputs and information outputs between a user and their digital mediums. So, in this context, haptics is the input modality to the user, just like any other sensory input like vision and audio. Human touch is strong and a dominated sensory medium. And the goal of haptic interactions is to optimize the capacity of sensory communication between the user and digital mediums through their devices. So in this context, there are several potential opportunities for haptic feedback during XI interactions. And here I'm highlighting just a few of them. The first one is the context of sensory feedback. So humans throughout their life use touch to interact with the world, and they develop internal model corresponding to their interaction with the objects and then their behaviors. For example, when a user squeezes a ball or slides a finger over a surface, they expect feelings of compliance of the ball or texture of the surface corresponding to the visual outlook of the object or their prior experience with these objects. Artificially creating these effects not only give user a believable experience in simulated environments, but also completes the action confirmation loop during their interaction with the digital world. The second category is sensory substitution, where sensory feedback through other modalities and across modalities are mapped as haptic feedback. For example, in one case, distant objects are projected on a haptic feedback screen and scanned by users through their fingers, or the expected feedback on the hand is translated to the wrist for the user to feel compliance of physical object that they're interacting with their hands. The third category is where haptic feedback augments typical user interactions to improve task performance, such as to improve, such as to increase their motor control during activities. And finally, haptic feedback can enhance user experience by giving them awareness about their own self, about other users, and about the surrounding objects and their behaviors. For example, animated haptic feedback can increase immersion during games and movies and modulate user behaviors and emotions in simulated environments. So there are many options and opportunities for us to add haptics in the haptic uh, in the XR domain. And what I want to see, I want to show a presentation of a technology landscape in the XR interactions. Here I'm showing technology readiness level on the y-axis, where the lower y is high, meaning that there are fewer challenges in enabling haptic technologies, and increasing y-axis indicates more challenges in the technology readiness level. On the x-axis, I define application spaces, where lower value includes fixed location applications, and moving right takes us to more ubiquitous user interactions. One common and practical utility of haptic feedback is perhaps in the grounded feedback devices, which restricts the user to a specific location. Nevertheless, it reduces the challenges in enabling technologies and produce high forces and displacement cues to the users. These devices are quite common in both academic and industrial settings. Perhaps the most common device in research has been grounded force feedback device, such as haptic feedback, such as phantom haptic feedback device, which provides relatively high forces to the user. Other applications have been investigated in surfaces, as Alison suggested earlier, like tabletops and interactive walls in human robot interactions, for in-home entertainment like gaming platforms and furniture, for location-based entertainment such as in rides, shows, and theaters, and also for mid-air interactions. The second class of devices are handhelds. Those are smaller in sizes and physical form and are ungrounded. The application space is quite broad and users can easily move them around. However, these devices render relatively lower forces and mainly because of lower in size and their power requirements. Inability to use hands for other activities. And, however, they pose more challenges in enabling technologies than grounded feedback devices. Main applications and product space are in the game controllers, cell phone technologies, tablets, stylus-based tools and markers, and toys, and there are a few others as well. The third class of devices are in wearable, which connects with the user and give them freedom to move around and perform other activities. However, the technology readiness level to enable haptic feedback in wearable devices is low and quite limited. So applications that have been explored and implemented are in gloves, palm straps, wrist and forearm bands, eyewear and head-mounted displays, clothes, belts, shoes, and even in soft, flexible on-skin coverings. So combined together, these classes of devices open up various opportunities of haptic feedback in the XR landscape. However, as the applications become more ubiquitous, the challenges in technology readiness are higher. So big challenges. So here I put these challenges into some perspective, although these are not the complete list, they are just a subset. But as going through the earlier talks, we saw that the biggest challenge is perhaps in the hardware domain. We're reducing the size, weight, and power of devices in a compact form factor that can render haptic signal with sufficient fidelity and transparency have utmost importance and challenging feat. Putting these technologies in an acceptable form factor for comfort, user mobility, and appearance for social acceptance are also challenging problems for haptic feedback technology. The cost of technology also adds up financial challenges, and justifying added value against the cost sometimes becomes challenging. The second class is infra, and technical challenges occur during integrating actuators with sensors and human users. While reducing the interference, noise, and structure resonance are worked through, lack of testing protocols and standards for testing and validation also limits the technology advancement during device development. Another challenge is to find the technology that renders reliable and repeatable signals and is manufacturable in scale. Scarcity of software tools and framework also slows down the flow of information between haptic device and XR software stack and defined use cases. And undefined interaction models between sensor data and haptic output pose limitations in defining valued use cases between various sensors and actuation technologies. And finally, our limited understanding of touch perception and how low bandwidth and low fidelity tactile signals can replace kinesthetic feedback, and how to create consistent perceived response by the population also limits the use of small and compact device technologies. In addition, there are challenges related to coupling interfaces, skin health, and user safety, while using the device have also slowed down the widespread of haptic technology for everyday and everywhere use cases. These challenges are not uniform across the XR spectrum, and grounded devices have generally fewer challenges, while handheld and wearable devices had opened up a new set of challenges. These challenges are just subset of what resonates with other speakers, and bring new opportunities for us to solve them. Here, I will go through two case studies on how we can overcome some of these challenges using technologies that are already available. Particularly, the first one I will talk about is stereo haptics that utilizes off-the-shelf actuators and sensors a- and audio-based tools to author and control the haptic information flow and enable high-definition haptic feedback. The second is to use a common screw-based machine component to devise a compact and high bandwidth haptic actuator and use current XR stacks to enable valued use cases. So let's go with the first uh, case study. So perhaps this project has nothing new, and probably many folks working in haptic already uses some of the stereo haptics framework. However, the significance is that it assembles various known facts under one framework and enables quick prototyping in haptics using already established tools and technologies. Similar to stereoscopic and stereo sound system, the stereo haptic system using two or more haptic actuators to create an illusion of moving and high resolution haptic feedback. The framework utilizes an audio-based framework, which is available and almost and which is available in almost every computing device. Audio tools are highly matured, and audio workflows and work streams are well established in various industries. So if you take a typical computing device such as our computer, it is equipped with two channels of audio output to drive a pair of speakers and one single audio input for the microphone. We can use the same audio outputs to drive haptic actuators and use the audio input to measure user activities. We prototyped a board using off-the-shelf components that cater audio input and output to enable haptic feedback and work through typical audio-based tools to quickly prototype user applications. The board includes a pair of D-class audio amplifiers and a preconditioning circuitry for sensor input that are directly plugged into audio ports of a computer or your cell phone or basically any other device which has these ports. So the question is why stereo haptics is important. So just looking at the spectrum, there are various haptic actuators that are fundamentally voice coils. As Jeremy and Heather mentioned earlier, they are basically speakers and are directly controlled by alternating audio output. Moreover, various audio interfaces and amplifiers are available off the shelf that can enable multiple audio inputs and outputs, and there are plethora of audio tools to process, author, and route audio media, and we can use these tools for haptic content design and control. In addition, various sensors can be used as input with our driver board to track user movement, their internal states, and activity. Finally, novel actuators novel actuation technologies such as electrovibration, DEAs, and muscle stimulations also utilize alternating driving voltage with high voltage driver and can utilize the stereohaptics framework. So what does stereohaptics enable? So we ran a psychophysical study to determine if two actuators on various parts of the body create illusion of virtual sensation in between the two actuators. So we tested four mounting configuration where these voice coil actuators were placed along the continuous skin of the forearm, on two hands, across the head, and on two ends of a surface. We tested three types of illusions. In the first illusion, simultaneous stimulation at two actuation points create an illusion of a virtual actuator in between. In the second illusion, sequential stimulation separated by a time interval gives an illusion of moving tactile stroke between the two actuators. And the third is saltatory illusion, which gives an illusion of jumping sensation equally spaced between the two actuators. So here are the results for 10 participants. The four rows show actuator placement configuration. X-axis represents the temporal separation between each burst of vibration, and Y-axis indicates the number of actuators that participant felt, three or many. As you can see, all users felt multiple moving actuators in all four configurations. Yep, I don't have a slider. Uh, Anyways. As you can see, all users felt multiple moving actuators in all four configurations with the apparent tactile motion. However, the other two illusions were more prominent on the arm and surface than on the head and and on the hands. So we then used the framework to prototype various hardware and use cases, and ran several workshops where users were given the stereohaptics kit and asked to create application using their computers in a day to half day long workshops. Participants came with a wide variety of creative applications and use cases and demoed them at the end of the session. Some of them are shown in the picture on the right. So, in summary, stereohaptics provide an audio-based established framework to cater for haptic feedback technologies. Two or more actuators create multidimensional illusion all across the body, and these tools can be used by novice users for quick prototyping of haptic experiences. So, if you're a new researcher and interested in prototyping or playing with haptics, then you should read more about the framework in the paper, and also check out the link to supplementary material for Gerber files as well as sample activities. And I strongly recommend to stay for the intro to syntax session after these talks that also creates tools to work in haptics using audio-based devices and tools. So let's go into case study two. So the second use is for handheld technologies. Unlike grounded devices, handheld devices are mobile and untethered. They have small space and power requirements, and they are lightweight, so the device can be easily carried to places and move around during interactions. So the objective of this project was to realize a device that has a single axis of broadband motion. It is small, compact, lightweight, and requires low power consumptions. It has low number of moving components. It must have robust and repeatable performance, and is highly scalable in terms of engineering, production, and XR applications. So for the single dimension actuator, we started with exploring the design space, and it was quite broad. And whether it is integrated in a hand controller or in a cell phone or placed in a marker or head-mounted display, various haptic feedback cues can be rendered to the user. So we started with the prototyping the actuator and looked into various mechanisms using off-the-shelf technologies. We converged on the lead screw design based on its compact form factor and reduced number of components. Plus, the engineering to improve the efficiency and production in scale is well established, so the risk to move them into productization are relatively low. In fact, our lead screw actuator, Chasm, has a motor, a pair of bearing, a custom lead screw, a nut, and a saddle that works as a skin interface. The motor is driven by a motor driver, and displacement is monitored by a linear encoder, all packaged into a compact form factor. The video here shows the performance of Chasm with various displacement profiles. This is cool. So after building the actuator, we went into characterizing the actuator along engineering axis. So more information is given in the paper, but I will just highlight a few of them here. That the displacement tracking profile in free and loaded configurations were pretty good, and the response time was relatively fast, about 30 milliseconds. The device has instantaneous blocking force of roughly 3 Newton. However, this blocking force increased to roughly 5 Newton within 1 second of applying the force. The device bandwidth was sufficient, and users can perceive more than roughly 120 hertz of signal. The power consumption was also relatively low, with power stayed within zero point 0.5 watts RMS in nominal operations. So we implemented a software and firmware framework that are already available and that are already available, and used a USB-based HID mode to communicate between various devices and our Chasm unit. We implemented and evaluated the device and user studies and interactions using the Unity game engine, and made custom protocols in the Unity editor to author and control the flow of haptic feedback. With Chasm, we realized two embodiments, one in a head-mounted gear that individually controls two sides of the temple, and the other one in a handheld marker for rich VR interactions. With the first prototype, we tested participants in a navigation task where haptic cues on the temple indicated participants to move left, turn right, or turn backwards. Virtual environment is a maze-like office space, and the task was to reach to the destination meeting room as fast as possible. Each participant was tested in three conditions. In condition one, participants were given a map with randomized orientation and location, target location. In condition two, both the map and the haptic guidance cues were presented. And in condition three, haptic gating cues were presented, which mimic walking and running during this virtual task. So more results are in the paper, but here I'm just highlighting two figures. So in one case, the guiding haptic feedback on the temple significantly reduced the completion time compared to no guiding cues. And also haptic gating cues yielded lowest level of nausea, indicating that haptic cue may have reduced the motion sickness in the moving virtual environment. With the handheld prototype, we evaluated influence of skin stretch on perceived stiffness of objects in virtual environments. Usually, a grounded force feedback device renders various object stiffness, and we wanted to see if low skin stretch forces can represent some form of physical features of objects. So in a trial, participants were presented with two buttons that they pressed and indicated which button had a higher stiffness. Three test conditions were tested with 13 participants. In the visual condition, a pseudo-haptic feedback was presented in which the hand movement is scaled uh, to give an illusion of object stiffness. In the haptic condition, the skin stretch corresponding to stiffness of the button was rendered, And in that visual plus haptic condition, both pseudo-haptics plus skin stretch conditions were rendered simultaneously. Details of these rendering schemes are again presented in the paper. So the results show that the visual haptic condition yielded low stiffness threshold compared to the visual only condition. However, there was no significant difference between rendering visual plus haptics and haptic only conditions, indicating dominance of skin stretch cues in rendering virtual stiffness over, over visual only feedback. This indicates that the object dynamic features such as stiffness can be rendered using the tactile skin stretch cues. Finally, we created a palette of user interaction in where the user could feel surface features and texture, shapes, stiffness, inertia, etc. So you can see the video with John interacting with this virtual content. So these two surfaces have two different texture. You can draw a texture, and based on texture, you can map different type of haptic feedback to the texture. You can feel the shape, you can feel the stiffness of virtual objects. And then combined with the pseudo haptics, you can also feel the inertia of different virtual objects in the virtual environment. So what can we do with this? So our current CASM unit has about the volume of 6.93 centimeter cube, but we have prototype made it smaller and reduced the volume by roughly 1/4 of that volume. And I can show you a quick picture. If you can see me, this is the newest version, and this is the voice coil that was presented in previous talks that other folks have used. But this actuator itself is quite tiny. So if you want to know more about this work, please you can access the paper and the videos at ACM Digital Library. John's Sky presentation is also online, and if you're interested, then you can also view it. So in conclusion, haptic feedback extends the physicality of digital content in XR. Form factors ranges from grounded, handheld, and wearable embodiments for a wide variety of XR applications. New wearable technologies are in dearth. However, research is progressing. Current established infrastructure and hardware software stacks can be utilized to enable haptic feedback in XR landscape. And more investigations are needed to understand haptic illusions to enable rich and enhanced interaction in dynamic digital content, with dynamic digital content. So finally, I want to conclude, and I'd like to thank my colleagues and co-authors. Also want to thank Facebook and Disney for supporting me and my research. And finally, I'd like to thank the speakers for great talks, and everyone best of health and success in these challenging times. With this, I conclude. Thank you.
Thank you, Dr. Israr, for that great talk. I think once we get up to our syntax workshop, you're going to have a lot of things that you're like there.